Hello, everyone. Welcome to the sixth lecture of the seismic module. Today we are gonna deal with the second part of the functions and calculus. There's another one to finalize this subject, which we are doing in 2 weeks' time. Today we are dealing with functions and calculus. Okay, a bit of the context. I heard that you, some of you might have a bit of issues with the context. So we are mentioning the Michaelis-Menten kinetics, the equation of the Michaelis-Menten, and then we are moving into a discussion of the Hill equation, which is a general form of the Michaelis-Menten. We are going to explain the differences in a few minutes. And then we are gonna do a MATLAB implementation of the Hill formula. The next step is to get the first and second order derivatives, which is the main topic of this session. And this will help in the next session as well. And so we are discussing how these things connect and how they help us in modifying and adjusting things with ease once we know these features. And then we are going to use the multi-panel plots to plot the first and second order along with the Hill equation. And that's where you'll understand how these things connect. And last but not least, we are gonna solve the function and get the turning point of the equation. But let's start, and we are gonna see it in a few minutes. Starting with the Michaelis-Menten kinetics, I just took a couple of notes there for you. We are going to share the code with you at the end of this lecture, so you'll be able to read it yourself as well. And if you need some more information in terms of the context, first of all, try to Google it. Otherwise, just ask directly in the forum. So Michaelis-Menten kinetics is one of the best known models of enzyme kinetics. And it's basically an equation that describes the rate of enzymatic reactions. And it takes into consideration the product and the substrate. And it basically describes how fast a metabolite or a molecule is converted in a biochemical reaction per unit of time. The formula is given here, which is basically the rate which equals to V max times the substrate, and then divided by K plus S. Vmax is the maximum rate achieved by the system. K is the Michaelis constant. S is the substrate concentration. And what you see there is called the Michaelis-Menten equation. Let me get to the Hill equation, and then we are going to relate it to the Michaelis-Menten one. Basically, it's a general form of the Michaelis-Menten. Their difference are the ends that you can see there, which is the Hill exponent. Let me take it from the beginning. The Hill equation reflects the binding of ligands to macromolecules as a function of the ligand concentration. A common application of the Hill equation is modeling cooperative enzymes, and the formula is given as you can see here. It's basically the same as the Michaelis-Menten one, but this time we've got the substrate and the constant K, the Hill constant, to the power of n. and n is the coefficient, is the Hill exponent, which basically indicates the degree of cooperativity. It's basically a modifier that allows us to adjust how exactly does the substrate concentration enter the rate law. S is the substrate concentration, K is the constant, as said earlier, which is analogous to the Michaelis constant one, and Vmax is again the maximum rate achieved by the system. And the highlighted equation here is the Hill equation. I'm not sure why I've got these issues with MATLAB at the moment. Yeah, in terms of this part of the equation, we use it to, I mean, in the equation, to introduce a limiting term that will prevent the function from going to infinity. Mathematically wise, it's fine to have something going to infinity, but in terms of the real world and in the biochemical reactions, they don't go to infinity. They are limited by certain requirements, like the speed with which molecules can diffuse in a cell. That's the reason we are using this part of the equation in order to prevent the function from going to infinity. Overall, Hill equation is very powerful as a function for modeling rate equations, and by using the knowledge of Vmax and Kn, the function can be adjusted to the need of the experimental case. So based on the case we need to solve, we'll adjust this equation and be able to solve it. Let's now proceed into implementing the Hill formula. We are going to see this formula in MATLAB. Basically, what we do is what we've seen in the previous lecture. We are using an anonymous function to create the Hill equation. We are naming a variable with the name Hill, and we are assigning the equation into this variable. So we are using the anonymous function. At here, we are mentioning the variables, the values that we are gonna use, which is S for substrate, Vmax for the maximum rate. We are using K for the Hill constant, and N, which is the exponent, the Hill exponent that we are gonna use. And then we are just typing the equation. It's the same as the one we've seen earlier. So it's Vmax times S, and all these are divided by K at the power of N plus S at the power of N. You might have noticed that we are using those dots here before the arrow, which denotes the power, before the division sign. And you might be asking, you might be wondering, why are we using the dots here? And I'm explaining below. I took those notes. Basically, we want to plot the function later over a specific range, and because this range is not continuous, it's a discrete one, which means there are a lot of values. The operation will be processed element-wise for every single value. That's why we use the dot before the process, before the operation, so before the power or before the division here, in order for this operation, for the division, for example, to occur for every single value. Otherwise, if we don't use the dot, this operation is not gonna work as we want it to. Then we are trying to see this this equation, to solve this equation using some values, some specific values. These were taken from the textbook here, which is for the maximum rate number 10. So 10 is the maximum rate of this equation. Then we've got k, the constant, equals to 1, and the n, the exponent, is again equal to 1 here. If the exponent is equal to 1, that means that the Hill equation is the same as the Michaelis-Menten equation. If I go back and we compare those two, if we compare the two equations, the one you can see here and the one below, you can see that the only difference is the power of n. So if the power of n is 1, if n equals to 1, the power of 1 is again the same. So the Hill equation is converted into the Michaelis-Menten equation. It's basically the same. That's why if we use n equal to 1 here, the Hill equation is the same as the Michaelis-Menten equation. Let me try to run at least this part. I'm gonna plot it as well. I'm giving the limits here from 0 to 5, can be from 0 to 3 or whatever. And let me plot it here so you can see what this equation looks like. Sorry, my MATLAB is a bit slow. I have to restart it, but I think we are gonna be fine for now. So this is the shape of the Michaelis-Menten equation and the Hill equation, but in the power with the exponent n equals to 1. Here I'm not explaining. Let me have this on the side. Here I'm not explaining. I mean, verbally, how what the F plot is, etc., or what the line width is, because these are what we covered in previous lectures. But if you've got questions, stop me and ask directly, or ask your questions, or later on your own time, run through the previous lecture. And if you still have questions, ask directly at the community. I mean, online in the Seismic website. Yeah, what we did here is to plot the Michaelis-Menten equation, or basically the Hill equation, but with the exponent equal to 1. Let me open the limits to 50 and run again. As you can see here, not the rate, I mean, how fast it reaches the highest rate. It's because we've extended the limits to 50, but we can zoom in here and we'll get the same plot as before. As you can see here, that was the reason I extended it, is to show you that the rate, but yeah, it's this part should resemble the one that we had earlier. But let me get back to the limits of 50 again, so you can see that the line comes towards 10. So it reaches 10 or a bit below 10, and it stays there. That's not just by, I mean, it's not by luck. There's a reason why it goes to 10. It's because the y-axis here resembles the rate. And the highest rate that we defined in the equation was 10. You remember that we gave the Vmax here being 10? That's the reason. Let's give it now a different number of the exponent. I'm giving it a number 4 there. If I run and I'm naming the equation Hill 4 because I'm having the exponent equal to 4. And let's plot it and let's see how it looks like. I'm gonna this part of code all together. As you can see, I'm using the hold on here, which means that in figure 1, I will plot Hill 1, which is with the exponent equal to 1, and then using hold on in order to plot at the same figure the second plot, which is the one of Hill 4, which is the one with the exponent equal to 4. So let me run this all together, and then I'm basically naming the x and y labels, the x and y axis, with S in the x-axis for substrate and rate in the y label in the y-axis. And we've got this. As you can see, we've got the same equation as before. That's, I mean, the black one. We've got the same plot as before. This is the Michaelis-Menten one, or the Hill with the exponent equal to 1, and the Hill equation with the exponent greater than 1. As you can see, it's a sigmoidal curve, and I've colored it in a different color, magenta one, so you can see them both. What we are gonna do now, I mean, this was just to explore the equations and what's the difference between different exponents. Let's do another one, actually, with the exponent equal to 10. And I'm gonna plot it on the same plot. And you can see that the rate as the exponent increases, you can see that it reaches the highest rate earlier with less substrate. Less substrate is needed to reach the maximum rate if the exponent is greater. That's what we can see here. Let us now proceed to the differentiation of the Hill function, which is basically the main part of this lecture. I'm using clear and CLC to clear everything from the workspace and the command window. And now we've got a fresh workspace to start. We are defining the symbolic variables. This time I'm not defining them as we did earlier, as you can see, using the anonymous function here. And we are using the Sims function. The reason is because this time we are defining them as symbolic variables, not algebraic, as we needed it to be earlier. However, we are gonna convert it into algebraic later on. Let's come back to this in a second. So I'm using the Sims function, and again, it's the same symbols: S, Vmax, K, and N for the exponent. I'm running this, so we've got them all in the workspace. And then we are proceeding to define the function. Again, we name it Hill. And it's the same function as the one, is the same equation as the one we used earlier. This time we don't need the element-wise operation. You remember the dots that we were adding here. We don't, I'm not sure if I forgot to mention it, but this dot, when we need to use the element-wise operation, we add the dot before the operation. So it's before the power, before the division, before the multiplication, if there was one, before the sign of plus or subtract, if that's the operation we need. We just have to add the dot just before it. However, this time we don't need the element-wise operation because it's a symbolic operation. We are only dealing with the symbolic at the moment, so there is no need to add this element-wise thing, the dot. Running the function, the piece of code. So we've got the function, we've got the equation saved in the variable named hill. And now we are proceeding with the differentiation of this variable. The differentiation is being done by using the function diff, which is the differences and approximate derivatives. I've added below the link. It's the only link that I added today because everything else that we are using, we've seen it in the previous lectures, in any of the previous lectures. So we are using the diff function. We are mentioning the variable that we want to differentiate, and against what? Against fs, against s. So we are saving it on a variable named hill diff. It makes sense. It's the differentiation of the function hill. So I'm running this part of the code, and we usually always, I always do that. We use the simplify function as a routine after, every time I use the diff function, I always use the simplify after that, just to check that if there's a simpler version of the equation. So I'm using the simplify function. I'm not mentioning it below because we've seen it in the previous lecture, and that's how it should look. This is the simplified version of the first order of the hill function. The first order derivative of the differentiated version of the hill equation. And now we are ready to plot both the function in its original form, the hill equation, which is that one, and also its first derivative, which is the one that we created here using the differentiation function and then simplified it. So the simplified form of the differentiation of the hill equation. So we've got the original form and we've got the first order derivative that we are gonna plot. In order to plot it, and then I'm gonna explain what's the connection between the two. So what's the first derivative, the first order derivative, compared to the function in its original form? What's the connection between the two? We are gonna come back to this in a second. So in order to plot it, we first need to convert the symbolic into an algebraic function. That's what we did in the previous lecture as well. So you should be familiar with the MATLAB function here. So I'm naming the new variable Hill algebraic because that's what we are gonna convert it to, an algebraic function. And the variable that we are converting is the Hill, which was defined earlier as the Vmax times S over K plus S, each in the power of N. You might remember from the previous lecture that in the MATLAB function, we first mentioned the variable that we need to convert into algebraic, the symbolic variable, the symbolic function that we need to convert into algebraic. And then we are mentioning the variables. It's vars in inverted commas, and then there's a comma, and then we mention the variables that we are going to use. In this case is S, V max, K, and N, which are the parameters that we've been using in the Hill equation. And in the same form, we are converting into symbolic, the symbolic function into an algebraic function, the same way in the differentiated version of the Hill equation, the first order derivative, basically. Using again the MATLAB function, the Hill differentiated variable, and again, the variables are the same. So I'm running this part of the code so we can create the algebraic functions. You can see them in the workspace here, Hill algebraic and Hill differentiated algebraic. And then we get the functions with specific parameters. Instead of having S, B max, K, and N, this time we are having the actual parameter, actual values for the parameters, 10 for the Vmax, for the maximum rate, 1 for the constant K, and 4 for the exponent. It's not 1, this time it's 4, so it's it should not be the same as the Michaelis-Menten. You remember what we've seen earlier. Again, we are using this function, the anonymous function, and we are naming it fun1. I mean, I took a note here, fun comes for function. You can name it whatever you want. You can name it fun Hill algebraic, or fun2 can be fun Hill diff algebraic because it's the differentiated version. But anyway, I'm naming it fun1 and 2. And I'm getting the functions with these specific parameters here. We are gonna plot again the figures. So I'm first specifying the limits as we did before, from 0 to 3. Or actually earlier we had it to 5, but yeah, 3 should work as well. And then we are proceeding to plot the Hill function and then to plot the derivative. As you might have seen here, I'm using figure and then number 2 in the brackets. So I'm creating a new figure named figure 2. And you might have noticed here that I'm using the subplot. It's in order not to plot a single plot for each of them, but to plot them all in one plot, all the curves in one plot. And I'm distinguish them in 3 panels. So I'm going to have 3 panels, one below the other. At the moment, we are going to have just 2. In the normal form, the Hill equation in the normal form, and the second is going to be in the first derivative. but I'm creating 3 panels because later on I'm gonna create the second derivative as well, and I'm gonna place it there. Let's see how it looks like. First of all, to create the figure and the 3 plots, the 3 subplots, and then using the F plot again. So you've seen this is the first panel, second panel is gonna be below, and then the third panel is gonna be at the bottom. So in the first panel, I haven't, that's the initial template one. I haven't plot anything yet. We are gonna plot the function 1, which holds the Hill equation with the specific parameters 10, 1, and 4, and we are gonna solve later for S. So I'm plotting it using the limits that I defined earlier from 0 to 3. And I'm increasing, I mean, the color is red, and I'm increasing the line width to 2, so it's easier to visualize it, to view it. Yeah, let me have that on the side. And yeah, as you can see, we've got the sigmoidal curve as we had earlier, with the limits from 0 to 3, and you can see that at some point it reaches the maximum rate, which is 10, and it's close to 10, and it stays there. I'm increasing the limits, the axis limits from 0 to 10 this time, and adding the Y and X label, naming the Y as Hill. Then we are gonna have the D Hill, which is the differentiated version of the Hill, and then the square, D square of the Hill. But yeah, let's see it in a few minutes. So I'm having the limits from 0 to 10, so you can see that it reaches 10, and in the y-axis it's the Hill, in the x-axis it's the substrate. The Hill, by saying Hill, I mean here is the rate, the y-axis is the rate. I'm just naming it Hill because the second and third panel are gonna be named the first derivative of Hill and the second derivative of Hill. So subplot, again, I'm using the subplot 3, 1, 2. 3 stands for the number of the panels. 3, we've got 3 panels, as said earlier. 1 for the column, so it's the first column, and 2 for the row. So we are going into the second panel, which is found in the second column, in the second row. And you can see that it's been put here. It's empty. We haven't plotted anything yet. We are going to plot it now. So it's again the same f plot, the function that we are using. We are using the function number 2 this time, function 2, which is the differentiated version. So it's the first order derivative of the Hill function. And I'm using again the limits from 0 to 3. I'm always using the same limits for the panels to be comparable. I'm just changing the color into blue, and yeah, I'm naming the substrate, the x-axis as substrate, the y-axis as D Hill, which stands for the first order derivative of the Hill equation. And let's plot this as well, and this is how it looks like. So the first order derivative, which can be seen here, shows the slope of the original function. You remember I told you that we are going to discuss how these two are connected. The first derivative is the slope the first order derivative of the original function is the slope of the original function. It determines the slope of the original function. You can see here that from 0, or basically from this point, let's say, the slope starts increasing again. And then from a point onwards, which seems to be here, from that point onwards, the slope starts decreasing again, decreasing until it reaches the maximum rate. Okay, this is what we can, this is what we can see here, that the slope is increasing up to this point here, which is in line with what we've seen in the red line, and then it starts decreasing. So the blue line here, the first order derivative, describes the slope. The slope is increasing up to this point, which we are gonna be finding later what this point is, and then it starts decreasing again until it reaches 0, because the original one, it has reached the maximum rate, which is equal to 10. So the inflection point is where it turns from increasing slope to decreasing slope. So it's basically the exact point on which the transition from the first state to the second state occurs. I think I've mentioned this. Yeah. So the inflection point is the exact point on which the transition from state 1 to state 2 occurs. Is basically the lower state to the higher, to the lower state to the upper state. Yeah. So up to this point, as mentioned earlier, the slope was increasing, and after that, the slope started decreasing again. We already mentioned that. Now we are gonna proceed to the second derivative, the second order derivative. And basically this is the curvature of the original function. It's basically the slope of the slope. So this time we are gonna describe the slope of the blue line here, of the blue curve here, which is the slope of the red line on the top. The way we do it is the same as we did it before. We just use the, we are having the symbolic differentiation, again using the diff function, but this time we are differentiating the already differentiated version of the Hill equation. So we are differentiating the first order derivative. And we are ending with the second order derivative. And this is the symbolic differentiation. And then we'll need to convert it again into the algebraic function, convert the symbolic to the algebraic function. As said, before doing that, by creating the symbolic function, by using the differentiation function, we always use the simplify function as well, just to get it into the simplest possible form. Then, as we did earlier, we are using the differentiation, the MATLAB function here, to convert into the algebraic function. It's the same as we did earlier, and using specific parameters, we are creating the function tria. All the time we are using the same values in order to have the functions comparable. Let me run this part of the code as well. And now we are gonna plot the third panel. That's why we've got 3, 1, 3, which means 3 panels, first column, third row. So at this position here, we are going to plot the second derivative. We do that by using the fplot function. We are naming the function 3 limits. This time I'm making it magenta, so it's a different color. Line width, it's the same. The limits are always the same to be comparable. Sorry. And I've plotted it. I'm naming it D2 hill, which is the second derivative of the hill equation. The x label is S. I'm not gonna add the line yet. And you can see here what the second derivative looks like. I've added a lot of comments here. Let's go through them together. Yep. So yeah, we need to discuss how the first order derivative relates to the original. We already did that. We said that this is the slope of the original. And we also need to discuss how the second derivative relates to the first order derivative. With a note on the inflection points. That's what we did, but let's see it again here. At the, yeah, as said earlier, the slope is increasing up to this point, as you can see, and then there's the inflection point, which is where the maximum point of the first order derivative is. And after that, the slope starts decreasing. That's what happens in the original form. The slope starts decreasing after the inflection point until the rate reaches the maximum rate. The same implementation can happen, can be seen in the second order derivative. The slope is increasing up to this maximum point here. As you can see in the blue line, the slope is increasing up to this point here, which is the same as where the maximum here is. Then it starts decreasing again until it reaches this maximum. So the slope decreases again until this turning point, where it starts increases again to create this minimum point. So the slope decreases again until it reaches 0. And here it increases. I mean, there's a turning point here. And from this turning point on, the slope starts increasing again until it reaches 0. Let me plot that line. As you can see, I'm plotting this line between the limits from 0 to 3. So from 0 to 3, and it should always be the line at 0. So it's gonna be a straight line at 0. In order to show you, yeah, you can see it here. In order to show you when the magenta line reaches 0. So we can see that at rate equals 0, the line crosses, the magenta line crosses 0 at the plot for the second order derivative. And there is the maximum point of the first derivative, as you can see here, where it crosses 0 in the second derivative. In the first order derivative, it's a maximum point, and it's the turning point. It's the inflection point of the equation in its original form. This is the relation between the three equations. The reason we are particularly interested on this inflection point is that in any system, be it neutral networks or biochemical models, etc., we are always interested in where this change of state takes place. You remember we talked about the lowest and the highest state. We are interested in where this change of state takes place formally, so we can distinguish or classify the states. And we always refer to this inflection point, and we are mentioning left or right of the inflection point. And in the next section here, trying to have the solution for the inflection point and see where this what's the value of this inflection point. We do that by using the F-solve. We've discussed this in the previous lecture. So we are aiming to see the substrate at the inflection point, and we can only do that from the second derivative function. So we are using the fan3, which is the second derivative function. Before doing that, as you can see here, we are solving against what? We are giving what initial value. That's why before executing this part of the code, I'm doing an initial guess. I'm giving a random value to start with, a starting point of the substrate 0. I'm having it equal to 1. So the substrate at the infection point will be solved using the initial substrate equals to 1, as you can see here, as 0. Let me run this part of the code, and the number 0.8801 is where the inflection point occurs. And as you can see here, I'm not sure if I can magnify it. As you can see here, the we cannot see it like this, but anyway, the inflection point can be seen here a bit before 1, which is basically 0.88, which is what we've found by solving against this. Then from the original function here, that's why we are using function 1, we can see the rate of inflection point. As said earlier, the rate can be seen from the original the equation, the curve from the original equation is showing the rate. The second, the curve of the first derivative is showing the slope of the rate, the slope of the previous one. And the third one, which is the second order derivative, is showing the curvature. So if we are dealing with the rate, if we want to see the rate at the inflection point, so the rate, what's the rate here at 0.88, the value of substrate, what's the actual rate at that point, at the 0.88, we have to solve using the function 1 to find what speed is achieved at the value where the inflection point is. Function 1 is being used, and then the inflection point here, which is 0.88. And we can see that the rate of inflection is 3.6 3.75. So at 3.75 here, the inflection point takes place, and 3.75 is the rate, is the speed at which the inflection point takes place, which is where the first phase goes to the second phase, the lower to the upper. And in order to see that, I'm using a subplot 3.1, which is the first one, and I'm plotting a line in the rate of inflection, a straight line in the rate of inflection. So you can see it here. At this point, which this line crosses the curve, is where 3.75 is the value of the rate, and 0.88 is the value of the substrate. I'm gonna leave it here. Okay, yeah, the next, you don't need the next thing. It's basically I'm plotting them all at the same plot, but yeah, this one is much clearer than that one. So this is what we should have explained today. In the next lecture, we are gonna see how we can use what we learned today into further analysis. I hope it was not too confusing today. And if you, have another look, rewatch what the recording that we are going to upload. And if you still have questions, ask in the online forum in the Seismic website, and we are going to come back to you. Thanks very much for your time, and I'll see you in the next lecture in 2 weeks' time. Bye-bye.